Welcome back to linear algebra. In this video, we're going to be taking a look at Euclidean vector spaces. You are almost certainly already familiar with the geometric vector spaces, which is specifically the Euclidean vector space in the plane, two-dimensional vector space, and the vector space in the three-dimensional space in which we currently live. For this course, we don't want to restrict ourselves to just two- and three-dimensional spaces. So we're going to be looking at the generalized Euclidean vector space, or the n-dimensional space. So let me get my head out of the way, and let's take a look at the n-dimensional Euclidean vector space, which we often write as R superscript n. You can think of an element in Rn, vector x is in Rn, means that we can write vector x as the ordered n-tuple, x1, x2, all the way down to xn. Or, as we've mentioned previously, we can also think about vectors as column matrices. X is the matrix with entries x1, x2 down through to xn. And thinking about vectors in terms of matrices is going to be very much more convenient for us throughout this course. A vector space is a set equipped with a couple of specific operations that have specific properties. The first of those operations is vector addition. If I have two vectors, that I want to add together, the rule for adding vectors in the Euclidean vector space is that you add entry by entry. And the important things to note about addition in the Euclidean vector space, generally speaking, addition in any vector space, are the properties that you're used to talking about in terms of algebra. We have a commutative property. We have an associative property. We have an additive identity. The zero vector in this case. So that when you add them, you get 0. 0 plus x is 0. And we have an inverse vector. The opposite of vector x is the opposite of Each element is the specific definition in Euclidean vector space. So that if you add a vector and its inverse, you get the zero vector. It's not a guarantee that these properties will actually hold for any arbitrary vector space. So you do have to look at the vectors and figure out, does it actually work? Does our definition of vector addition actually satisfy the commutative, associative, identity, and inverse properties? Likewise, we're going to have another operation called scalar multiplication. And scalar multiplication is defined in the Euclidean vector space. If you take some constant and multiply times a vector, you are going to multiply that constant times each component of the vector. It's not the only way to define scalar multiplication in ordered n-tuples, but it is a way of doing so. And it turns out that it's a way that gives us another set of nice properties. Turns out that this is going to be distributive over vector addition. If I take some scalar k and try to multiply it times the sum x plus y, I get kx plus ky. It's distributive over scalar addition. If I have two constants, that's not a letter. If I have two constants, k plus l, that I want to multiply times vector x, I can multiply k times x and I can multiply l times x and then add them together. It's commutative with real multiplication. If I want to multiply k times the vector l times x, that's the same thing as multiplying k times l times vector x. And we have the identity, which is the identity of real multiplication 1. 1 times x is equal to x. Again, there is no guarantee that these 8 properties will hold, so we do have to prove them. In the textbook, they go through the second one, the associative property of vector addition. I'm going to go through the distributive property for scalar, or distributive over scalar addition, part 6. The other parts of this you are asked to work through and prove on your own. But let's let vector x be the column vector, x1, x2, down to xn, and let k and l be reals. I forgot to put in x is an n-dimensional vector, n-dimensional Euclidean vector. So that is all we know. And we want to look at k plus L times x. By the definition of scalar multiplication, k plus L times x is k plus L times x1, k plus L times x2, all the way down to k plus L times xn. Now, inside that vector, k plus L times x1 is a bunch of real numbers. So I have the distributive property scalar addition, scalar multiplication. Then my next step, inside each of the elements, each of the components of this vector, I can use distributive property for real numbers and split that up as kx1 plus lx1, kx2 plus lx2, all the way down to kxn plus lxn. Now, I notice that this is written out as a whole bunch of components being added together. I can split that up and take all of the things that have k's and write them as one vector. And I can take all of the things that have l's and write them as a separate vector. I can do this using the definition of vector addition. In other words, going from the second line to the third line is not obvious, but it should be obvious to you that you can go from the third line back to the second line. And then finally, I notice in each of these individual vectors, they are a scalar product. K times x1, x2 down to xn, and L times x1, x2 down to xn. And finally, that column vector x1, x2 down to xn is the vector x that I started with. So substituting that back in, I get that this actually does distribute out to kx plus lx. Again, I encourage you to take the time to go through the other properties and write out what the proofs might look like for those. I think I've mentioned the definition of a linear combination in the past, but I would rather repeat it than assume and accidentally skip over it. If we have two vectors, x and y, then a linear combination of those vectors is any vector, let's call it u, which is a times x plus b times y, for real constants A and B. And pulling in linear combinations is the heart of linear algebra. It's in the name. Looking at how things interact with linear combinations is the interesting thing in linear algebra. An idea that you are probably familiar with is the idea of unit vectors. In three-dimensional space, we call these unit vectors I hat, j hat, and k hat. When we're looking at a generalized n-dimensional vector space, we're going to call it E sub k hat, which is going to be the kth entry is a 1, and all of the other entries are zeros. So E1 has the first entry as 1, and the rest zeros. E2 has the first entry as 0, the second entry 1, and everything else 0. And En in n-dimensional Euclidean vector space has a whole bunch of zeros and then the last entry as 1. The reason that unit vectors are so useful is that every vector in Rn can be written as a linear combination of E1, E2 through to En. So taking all of those unit vectors and taking a linear combination will give you whatever vector you'd like. And the proof of this is fairly straightforward. Consider the vector x, which is given as x1, x2, down through xn. And notice that if we take x1 times E1 plus x2 times E2 plus dot 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 plus xn times En, we get vector x. And that's exactly what the proof says, or the theorem says we can do. We've just done it. Yes, the proof is that straightforward, but it is not guaranteed. We have to prove it. We have to explain ourselves. One last idea of the Euclidean vector space is the idea of a dot product. More generally, this is the inner product. Dot is the particular inner product for the Euclidean vector space. We'll be looking in the coming weeks at vector spaces other than the Euclidean one. Some of them will have an inner product which is different from the dot product. So, right, generally in a vector space, you might have a mechanism of multiplying two vectors together, which is called an inner product. In the Euclidean vector space, the specific operation of the dot between two vectors satisfies the conditions of an inner product space. And you are familiar with the idea of a dot product. We define vector x dot vector y as x1, y1 plus x2, y2 plus dot, 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 all the way to xn, yn. And if we think about these as matrices, the matrix vector x transpose multiplied by the matrix vector y is the matrix method of handling the dot product. So there's two different ways of defining the dot product that give us the exact same result, or at least close enough. Right? The matrix method gives us a 1-by-1 matrix whose only element is the dot product. But that's not a distinction worth worrying about. And just like with the scalar or vector addition and scalar multiplication, the inner product has a couple of properties that you're already mostly familiar with. It does not matter the order. The dot product is commutative. I put the name first when I did this before. Let's be consistent about that. The dot product is distributive. If you want to take x and dot it with y plus z, you get x dot y plus x dot z. The dot product is associative with the scalar product. Kx dot y is the same thing as k x dot y, and is in fact the same thing as x dot ky. And finally, we have the positive definite property, which says that if I take a vector x and dot it with itself, I get something which is positive or 0. And on top of that, the only way to get 0 itself out is to start with the 0 vector. These 4 properties are the definition of an inner product. The dot product satisfies these properties, but again, something we have to prove. And the dot product, and in fact, any inner product, has a couple of other properties as well. If you try to dot a vector with the 0 vector, you get 0 out. is one of the interesting properties. Which again, I think is kind of obvious. So I'm not going to go through the proof, but I encourage you to think about the proofs of all of these. One or more of them might be showing up on the first take-home exam. I'm going to mention one other concept concerning vectors, but not go through and actually prove anything with it. And that is the idea that the idea of the norm of a vector or the magnitude of a vector. It's an interesting idea that really speaks to the geometry of vectors. It's something we'll be looking at a little bit later on. It shows up in our textbook alongside all the other properties of the Euclidean vector space. But when we develop a little bit more machinery, we'll actually be able to do interesting things with it. So I'm going to hold off talking about that until later. Next time, I'm going to build up on the idea of the Euclidean vectors and look at functions acting on Euclidean vectors, and specifically a class of functions called a linear transformation. Again, linear, whole heart of linear algebra, kind of something that we'll be focusing on moving forward. But for now, I'm going to wrap up this video. Thank you as always for joining me, and I'll see you next time.